Hello, welcome to my class. Dear students, today we are going to learn about Cauchy's mean value theorem in this tutorial. I hope this tutorial will be helpful for you to understand the theorem. And before this theorem, we have gone through Rolle's theorem and the Lagrange's mean value theorem. And in both of these theorem, we use single function fx, which are continuous and closed interval AB, and differential and open interval AB. But here in Cauchy's mean value theorem, uses two functions fx and gx, and both of these functions are continuous on closed interval AB and differential on open interval AB. And here we need to find the numbers c in open interval AB such that f dash c upon g dash c equal to f of b minus f of a divided by g of b minus g of a. And this theorem, Cauchy's mean value theorem, is also known as generalized mean value theorem. Generalized mean value theorem of first order, because here this uses only first order derivative. Generalized mean value theorem of first order, and it is called generalized mean value theorem because if in this theorem, if you take g of x equal to x, if you take g of x equal to x, the function gx to be an identity function, then this statement turns to be the statement of what's called Lagrange's mean value theorem. For example, if gx equal to x, then g of a will be equal to a, g of b will be equal to b, and also g dash of x equals to 1. This implies g dash of c equals to 1, because g dash of x equal to 1 means the derivative of gx is constant, so it doesn't depend on the variable. So g dash c equal to 1. Then what happens on the right side of this theorem, you can see f dash c upon g dash c. Now let's put f dash c with f dash c itself. G dash c means 1, no need to put, equal to fb minus fa, as they are, fb minus fa divided by, now g of b means b, g of a means a. Means you can see this is the statement of the Lagrange's mean value theorem. So Lagrange's mean value theorem is a special case, a particular case of Cauchy's mean value theorem. So this theorem is called the generalized mean value theorem first order. So now let's see how to prove this theorem. Then, and the proving method, the method to prove this theorem is quite similar to that of Lagrange's mean value theorem. Right? In Lagrange's mean value theorem, we had defined a third function. We defined a third function h of x, which was the difference of the given function fx, and another function y, which was actually y means this was the equation of straight line or the second line that joins the points a, f, and b, f, b of the curve. And in similar way, here also we define a function h of x. Now let's start the proof. Now first we define a function. Let's consider a new function. Let's consider a new function h of x defined by, now we need to define the function defined by h of x equal to f of x minus f of a minus fb minus fa divided by gb minus ga at times g of x minus g of a for all x that belongs to AB. That means we are defining this function on closed interval AB. And then we have defined hx in terms of fx and gx, you can see clearly here. And we are in search of function which satisfies the Rolle's theorem actually. In Lagrange theorem also we did same thing. Here also we are defining function fx so that h of x will fulfill the conditions of Rolle's theorem. And let's see, well, will it fulfill or not. The first condition is, let's see, continuity. The first hypothesis of Rolle's theorem, and we know that both fx and gx are continuous on closed interval AB. Both fx and gx are continuous on closed interval AB. And you know by the continuity property of function that sum of the continuous function and the difference of the continuous functions, or the product of the continuous function, or the quotient of the continuous functions is again a continuous function. So here you can see fx and gx are here, they are continuous on AB. So their difference or sum, whatever you see, will be again continuous on AB, isn't it? And next, fx and gx are differential on open interval AB. So is their differences, isn't it? Or so is their sum, isn't it? Hence you can see hx are both hx satisfies both hypothesis of Rolle's theorem, that is hx is continuous on closed interval AB and differentiable on open interval AB. Then we write here, since both functions fx and gx are continuous on closed interval AB, so hx is continuous on closed interval AB, first one. Similarly, being fx and gx differentiable on open interval AB, hx is also differentiable on open interval AB. hx is also differentiable on open interval AB. Then hx is also differential on open interval AB. Now, so both of the hypotheses of, that means first two hypotheses of Rolle's theorem have been satisfied. Now we'll see for the third hypothesis of Rolle's theorem, that was fa equal to fb. That means here ha equal to hb. And what will be the value of ha? Also from 1 you can see, from 1 h of a equals f of a minus f of a minus fb minus fa divided by b minus a, g of a minus g of a equals 0, and h of b equals f of b minus f of a minus, sorry, here is gb minus g, gb minus g, f of b minus f of a upon g of b minus g of a, and here will be g of b minus g of a, this also equals 0 since all terms will be cancelled here. Then therefore h of a equals h of b, means all the three hypotheses of Rolle's theorems have been satisfied by the function hx. Therefore, all the hypotheses of Rolle's theorem are fulfilled by Hx. So there exists at least one number, right? At least a number C in open interval AB such that h dash of C equals 0. Now we need to find h dash of C. For that we need first h dash of x. And how to get h dash of x? We have got from 1. From 1 we have got h dash of x equals h dash of x equals f dash of x minus, this will be 0, means f of b minus f of a divided by gb minus ga and its derivative. G will be 0, means here will be g dash of x. So what will be h dash of c then? Let's see. So h dash of c equal to f dash of c minus f of b minus f of a divided by g of b minus g of a g dash of c. Since h dash of c equals 0, let's substitute the value. What will we get? Or 0 equals to f dash of c minus f of b minus f of a divided by g of b minus g of a g dash of c. Now transpose on left side and do cross multiply. We will get, therefore, f dash c upon g dash c equals to f of b minus f of a divided by b minus a, and which is the required fact to be proved, and hence we have proved the theorem. Hence the theorem is proved. Hence the theorem is proved. We have found a number, so like that. Okay. Then here, what's the strategy? Strategy is quite similar to that of Lagrange's mean value theorem. We first defined a function hx is the difference by using the function fx and gx, and which satisfies the Rolle's theorem, and we use the Rolle's theorem and to get the required result. And now let's see some fact about this theorem. Okay, as I told you just before, if you take g of x equal to x, the theorem represents Lagrange's mean value theorem. And that is one of the facts about this one. Okay? Some facts. Number 1, if we take g of x equal to x, then g of a equal to a, g of b equal to b, g dash of x equal to 1, that is g dash of c also will be 1. Then what happens? Then Cauchy's mean value theorem, Cauchy's mean value theorem turns to be, or reduces to, let's say, reduces to Lagrange's mean value theorem as f dash c upon g dash c means 1 equal to f of b minus f of a upon b minus a is the first fact. That means if g of x is the identity function in Cauchy's mean value theorem, then this will lead us to Lagrange's mean value theorem. And the second fact, if fx and gx are continuous on the interval a to a plus h and differentiable on open interval a to a plus h, then there exists at least one number, a number theta in 0 to 1 such that f dash of a plus theta h divided by g dash of a plus theta h equal to f of a plus h minus f a divided by g of a plus h minus g. This is the angular version of Cauchy's mean value theorem. And we can have enough examples of how to verify Cauchy's mean value theorem for the given functions in the given interval. And verifying Cauchy's mean value theorem is to find a number in the given interval which satisfies the given conditions or which satisfies the result of the Cauchy's mean value theorem. For example, let's see. I've done a simple example. You can do it very easily. It's not a hard problem. Example. Verify Cauchy's mean value theorem for the function f of x equal to x square, g of x equal to x cube on the interval 0 to 1. And its solution is very simple. I think most of you can do yourself as well. The first one, is we have been given two functions here. So what we have been given? The solution is list here. Given f of x equals x square, g of x equal to x cube, where x belongs to 0 to 1. And first of all, to verify Cauchy's mean value theorem, both of these functions must satisfy the hypothesis of Cauchy mean value theorem. And you know there are two hypotheses of Cauchy mean value theorem. First one, both of the functions must be continuous on the given closed interval. And you know, being polynomial functions, that's the first hypothesis. Being polynomial functions, both fx and gx are continuous on closed interval 0 to 1. I mean, polynomial function, you know, this function has been represented by polynomial. This is a polynomial of degree 2, this is a polynomial of degree 3. Polynomial functions means, in polynomial functions, the variable will have only whole number power, isn't it? So this polynomial function will be undefined or will be infinite throughout the real line. So both of the being polynomial function, they are continuous on closed interval 0, 1. And for second one, we'll find a derivative. Also, f dash of x equal to twice x, g dash of x equal to twice x square. And both of the functions are differentiable, means f dash x also exists, 3x square also exists in between 0 and 1 in open interval. That means both f dash x and g dash x do not turn to be infinite or indeterminate form within the interval, that means within 0 and 1. So both of these exist on open interval 0 to 1. Means fx and gx are differentiable on open interval 0, 1. It means both hypotheses of Cauchy's mean value theorem are satisfied. Then what must be again then? And when these two hypotheses are satisfied, then according to Cauchy mean value theorem, now we must find a number c in the open interval 0, 1. But how to find? That c will satisfy f dash c upon g dash c condition that we have learned in the theorem. Okay. Now then let's take that number c. Let c belongs to 0 to 1 such that f dash of c upon g dash of c equals f of b minus f of a upon g of b minus g of a. Okay, f dash of c means you can see from f dash x, that means twice c. G dash of c means here you can see twice c square. F of b means f of ab means f of 1 minus f of 0 divided by g of 1 minus g of 0. Now let's put value. I'm solving here on the right side. Okay, then don't cancel c here, okay, because we are going to solve for c. Twice c upon twice c square equal to f of 1 means 1, f of 0 means 0. So 1 minus 0 upon, or g of b also same, 1 minus 0. Means if you do cross multiply, you'll get 1 only here, or you'll get twice c square minus twice c equal to 0, or if you take c common, twice c minus 2 equal to 0, or you'll get c equal to 1, 0. Next is 2 by 3 z. But here actually we are searching value of c in 0, 1, and since 0, 1 is open interval, so 0 doesn't belong to open interval 0, 1. That's why we will omit this one. We will be choosing 2 by 3. 8 c equal to 0 doesn't belong to open interval 0, 1. 0, let's say 0 doesn't belong to 0 to 1. Therefore actual value of c that we require here is 2 by 3, which is contained in 0, 1. Now let's see, isn't it? And now if you see here, we are able to find a number in the interval 0 to 1 satisfying the mean value theorem by Cauchy, isn't it? So these functions fx and gx satisfy Cauchy mean value theorem. Hence the theorem is verified for the given function. That means Cauchy theorem. Theorem means Cauchy theorem, okay? For the given function, for fx and gx, let's say. Okay, fx and gx, and this completes our solution. Okay, then you might be choosing other functions, or in your textbook or in any other reference books you can find such problems, and I advise you to solve those problems. And if any problem persists, we may discuss that online. Okay, thank you.